Hey math people, tangent planes and linear approximations. We just finished up the partial derivative. We're looking at that immediate application of it. So we did this very same endeavor journey, whatever, step-by-stepness with Calc 1. After you first learned the derivative, the very first thing you did after that was the tangent line. So we're just doing that same sort of progression. So we're going to start with that. We're going to start with the warm-up on the tangent line, jump to the tangent plane, do a few examples, connect it to what's called linear approximations, which is just some fancy way of just saying, hey, use the tangent plane to approximate nearby points, where if you don't want to plug in weird decimals, you don't have to. And then look at some talk on differentials. So differentials are still worth studying. And even more so with respect to the next lecture as well. Anyway, this video is for you, Andrew. So what does that mean? That means to pause when you need to, use the timestamps, maybe you just need the examples, who knows, and then to be patient with yourself. Let's math. So what is the equation of a tangent line generally? Hopefully you remember point slope. Thereafter, find the tangent line for this parabola, and then do so at 1. Draw it out as well. All right, 3, 2, 1. You remember this. So this is point slope, right? Just an equation of a line. Some people like the y1 on the left side. Those people are weird. No, those people are normal. I just like mine on the right. That's how I roll. Okay, and then we would just figure out what goes into play for m, x1, and y1. They usually give you the x1. You have to find the y1 by plugging it into the original. In this case, it's 5. And then you would find that slope by finding that instantaneous rate of change at that input. So that instantaneous rate of change can be found by using the derivative here. Just plug in your 1 and you get a slope of 6. So here's my line, 6 times x minus 1 plus 5, and its tangent at x is equal to 1. Old school, boring. All right, I think that you have the tools to figure out how to extrapolate this. I think you can already do it. So follow that same exact philosophy, but remember this time around, you don't just have one derivative, you have 2. So find your 2 separate partial derivatives, okay? And then just like how we had this like slope in front of your x minus x1 idea, see if you can do that with not just x this time, but x and y. And then, of course, instead of isolating your y, you will be isolating your next variable, z in this case. It's definitely that beautiful aspect of Calc 3 where you can just, if you've truly mastered Calc 1 and Calc 2, it's like this seamless transition from the tangent line to the tangent plane. So if you're just sitting on the sidelines thinking, what is he talking about? That's fine. All right, extrapolate, give this one a go. 3, 2, 1. So instead of taking one derivative, you take 2. You have partial with respect to x, partial with respect to y, and these will serve as sort of like your slopes for the x component and y component respectively. And then thereafter, you just have to find the, so it is assuming you plug in your 1, 2 to find those slopes, right? And then thereafter, you just have to find the actual output at that moment. So plug in that 1, 2 into the original function, and that'll serve as like your plus y1, but in this case, like your plus z1, giving you the tangent plane this time around instead of the tangent line. Yeah, so drawing a tangent plane, you know, is a 3D curve or 3D surface on a plane here, a sheet of paper, so it's a little hard to see that. But what we can do is we can actually graph it. Let's do that instead. So what we're seeing is at this point 1, 2, 3, we're just kind of riding along this pretty intense edge slope, right? That's a fairly fast slope. So if I were to just go ahead and plot this tangent plane at that point, I'm just touching, just in that instance of time, borrowing the slope both in the x and y directions, and then you know, getting that same philosophy behind the tangent line idea. So we can actually formalize this as the tangent plane equation. Here it is. Really, we're just taking that partial derivative with respect to x and y, plugging in your point of interest, so your x and y value of interest, to get your slope at those moments. Remember, your y minus y naught is just kind of tacked on as a secondary term to, or even it shares the same weight, so it's not really a secondary term, but in cadence or in tandem with x minus x naught. plus your constant of z naught. It is just taking your tangent line equation and adding a single term in that same fashion. Okay, so let's just do like a few examples, okay? So find the tangent plane to the elliptic paraboloid at 1, 1. So you're going to find the partials, you're going to plug in 1, 1, and then you're going to plug in 1, 1 into the original and slap it into the equation. That's the ebb and flow. It's just tangent line, but one extra step. 3, 2, 1. Not the world's worst problem of all time, right? So we found those partials, we plugged in 1, 1 into each of those, and those served as our like sort of slopes in some way. Thereafter, we plugged it into the original, and that's what we tacked on at the end. Let's do another. This one has a little bit more funk to it, I'm going to say. So give this one a go. 3, 2, 1. So yeah, we have a what do we have going on here? For the partial with respect to x, oh, I see what I did. I distributed the e to the x to both terms. It's just the same thing because e to the x, the derivative is e to the x, and this is just some coefficient to e to the x because it's a constant in the eyes of x. So really, it's the same thing for f of the partial derivative with respect to x. So that's probably why we see the same outputs, right? Yeah, the outputs are the same. So for the partial with respect to x and the original function. So our partial with respect to y, that would just be, you could distribute this e to the x to both. This plus 2 would just be a constant because 2 e to the x is a constant in the eyes of y. So you're just taking the derivative of this sign, which is cosine. And then e to the x serves as that coefficient. Plug in 0, comma pi over 2. You do get a slope of 0 for the partial with respect to y. That's totally fine. You can still plug and play that 0 into the original equation. This whole term just goes away. So you're really just getting like a single variabled planar equation as the tangent plane. So it's not a curve. I do want to see what this looks like, so I'm going to go ahead and graph it. Okay, this is just so much fun. Look at this. What a cool little like curvy ramp thing. So here's my read on how to get an equation that looks like this real fast, is that if you look at the x, z plane, you see the exponential, and that's kind of what's happening here. Z is equal to e to the x. And then, of course, you get that little wave as your y changes, right? So I don't know. You don't need to know what that looks like, but it's nice to, you know, see the intuition behind it. So here's our point of interest right here in blue. So if I come up with that tangent plane, you'll see that, you know, sure as y doesn't have any impact at that moment. What's the interpretation? That the change of y, the change of z with respect to y is 0. Yeah. Actually, let's take a look at those curves because that could be fun. What if we look at when x is fixed to be 0? So, right. That would be a slope of 0 for this sine wave, right? A slope of 0 for this sine wave. So when y changes, z doesn't, just for that instant of time. And then if I look at when y is fixed to be pi over 2, that's going to be that exponential. And then when x changes, z changes with that slope of 3. And that's because you have 2 of these terms. This is a constant, right, in the eyes of x. 1 plus 2 is that 3. Okay, so that's it for that. Now let's just extrapolate this just like a mini little step forward through linear approximations, which is not a wild idea. Here it is. You can just use the tangent plane. This is just the equation of the tangent plane. Don't be too mistaken or confused by this a and b. It's the same thing as x naught and y naught to approximate nearby values. So what does that mean? So find the linear approximation of this function at 2, 1. AKA find the tangent plane, and then use that tangent plane to approximate 2.1 comma 0.8 as an input. The idea being, if you try to plug this into this equation, it could be like not fun and stuff. So we're going to do a slightly less not fun idea. That's seriously the concept. So we really can't extend it all too much. I guess the biggest extension to it on like an application sense or front is that like, let's just say that your function is like very messy. or maybe is changing, and you just don't want your computer to run through the computation every time if it's like some crazy long function. So it may just be not a bad idea to just approximate nearby. So think in the landscape of like Taylor polynomials. It may just be good enough. So that's what we're going to do here. We're just going to, did I trigger anyone's war stories of Calc 2 just there? Anyway, we're going to go through tangent plane first and then plug into 0.1 comma 0.8 second. All right, 3, 2, 1. So you got the tangent plane, and then you straightforwardly plug in 2.1 and plug in 0.8. So the read on this would be, well, if I had f of xy, and this is me just like extending this concept out to the fullest extent that I really can, x squared plus xy and then plus y squared. This is what this looks like. So it's this like kind of angled elliptic parabola of sorts. So what I can do is, if I were to plug in 2.1 comma 0.8, this is like a computer, so a computer is going to have very little issue plugging this in. I wouldn't really use the linear approximation in this case like ever, but I could be mistaken. I'm but a teacher, and I am not on the job other than this. So anyway, you can see the approximation with the linearization is 6.7, which is pretty close to 6.73. And that's because this point is really close to this point. Of course, you wouldn't really utilize this tangent plane if it was like at 100 comma 100. That would just be way off, and that's just reckless and dangerous. Don't be too reckless with mathematics. Okay, give this next one a go. Here we're dealing with a function of 3 variables as our input. Find the linear approximation here. You will have some symmetry at play, so you could be a little creative due to the fact that the partial with respect to x, y, and z will all look kind of the same. So up to you if you want to use that fact. If you don't, no big deal. See if you can find the tangent well, in this case, it would be the tangent hyperplane, right? Because it's of 3 input variables. So use that extrapolation that I was hinting at earlier, and then plug in our ordered triplet here to determine that approximation. 3, 2, 1. All right, so you have 3 partials this time. Whoa. But they all kind of feel the same. So you can see here that the inputs kind of produce somewhat similar concepts here. It's somewhat similar numbers. And then if we were to plug in 4, 7, 4 into the original, you get 9. So we would end up with a tangent hyperplane of this expression right here, which is still just going to be a linearization of plugging in this ordered triplet because this point is so close to this point. So if you just simply plug it in, you end up getting 9 plus 11 over 90. So it's pretty close. It's a pretty close approximation. If we ever have a really messy function here and you don't want to just crank out numbers over and over and over again, you can use linearization to save some computation work. So long as that loss of accuracy is worth it, like it's okay to lose that accuracy. Okay, because there are certain situations where it's okay to lose accuracy and there's certain situations where it's not. So just be careful with that, future engineers. Okay, so single variable calculus, we knew that once as this just change in y over change in x. We would say that little tiny change, that little nudge was dy, and then with respect to that vertical change, and then the horizontal, just that dx. So you can say that f prime is equal to dy dx, branching together Lagrange notation with Leibniz. Well, what you could do is you can multiply both sides by dx here. So you can say the differential dy is equal to dx, but scaled by f prime. That's sort of one read of this. You can multiply both sides by dx to isolate the differential dy. If you were to do that in Calc 3, it's sort of like it's the same idea, just I kind of sell it as like kind of like the sum of partial derivatives now, because you have to add up all your change. So you have a change with respect to x and a change with respect to y now. So rather than it just being a simple single fraction and you can just multiply both sides by dx here, we have a little bit more going on because we were technically like multiplying both sides by dx and dy if you really wanted to think about it that way. You can also think about it this way. So these are all just intuitive, like you could think about it this way, chatter. Just to kind of make things a little bit more digestible, you could think of it as like, oh, well, the partial x cancels with the dx, and the partial, it doesn't quite work out this way. The partial y can kind of cancel with this dy to just get your sum of your partial changes. Anyway, so if we wanted to just kind of take this home, we could use this differential way of thinking to come up with linear approximations. So here is our last function of several variables, just 2. If I wanted to approximate f of 0.2, comma 0.9, I can use the fact that, well, this f of 0.2 plus 0.9, or f of 0.2, comma 0.9, is like f of 0, comma 1, just adding that like tiny little change in z. So that tiny little change in z being the partial derivative with respect to x times dx, so your change in x, plus your partial derivative with respect to y times dy, your change in y. So I'll show you what this is going to look like. You can play with it if you'd like to in 3, 2, 1. So it's going to look like this. Your dx, your change in x, is just 0.2 because 0.2 minus 0, so 0 is our input here, is 0.2. And then your change in y is 0.9 minus 1, which is negative 0.1, because that change from 1 to 0.9 is 0.1, but we're going from 0.9 to 1, so that's, or 1 to 0.9, so that's negative 0.1. Well, anyway, we can take the partial with respect to x and plug in 0, 1 to get 2. And we can take the partial with respect to y and take the derivative with respect to y to get 0. So now within this equation right here, right, or you can even look at this one, it doesn't really matter. You can see that there are 4 values we need to extract. The partial with respect to x at that point, and then dx, we have both. The partial with respect to y at that point, and then dy, we have both. Dx and dy were just found via subtraction. And then partial with respect to x and partial with respect to y, plugging in 0 and 1. That's our common ebb flow we've been doing for a little while now. You get that 2 and 0. Plug and play into that dz formula, and this is our small change in z to get that approximation. So I know that f of 0, 1 is just 2. So f of 0.2, comma 0.9 is going to be that 2, except plus that small little change. So 2 plus 0.4 is 2.4. So just another way to approximate nearby values, this time using differentials. Okay, that's all for today. Math on.